Afternoon, everyone. Welcome to another seminar. Today we have Professor Masoud Darabi. Professor Masoud Darabi is a Roy J. Leonard Chairs Council Associate Professor at the University of Kansas. He has bachelor's in civil engineering and master's in mechanics of structure and materials from Sharif University of Technology in Iran. He also has a PhD in materials from Texas A&M University, and his research interests include multi-physics constitutive modeling of materials, multi-scale simulation of distresses, micromechanical simulations, as well as asphalt concrete pavement technology and molecular dynamics. Professor Darabi also got a really luck today that the temperature outside is finally not so cold, and that's very nice. Thank you, Professor. And let's give him a round of applause.
You turn it on and then you click on the arrow down. I think that's better, yeah.
Good afternoon, everyone.
You
And thank you so much for the introduction. And thank you so much for the invitation. It is my honor to be here. My name is Masoud Darabi, and I'm at the University of Kansas. The presentation that I will go through today is mechanistic-based modeling of rutting response of flexible airfield pavements. But before I do that, I need to acknowledge those my mentors and those who actually did the work. I'm just presenting it. I've been very lucky to work with Professor Paris Little, Rashid Abu Iyad, Masoud, and David Allen, and my colleagues and some of my students, which are now my colleagues, Chenvi, Isa, Omid, Rashi, Mohammed, and Gaye. These are the people who actually did a lot of this work. Now, without further ado, let's look at the research that we do. We look at theoretical and computational modeling of flexible asphalt pavements, and in that realm, we look at constitutive modeling of rutting, fatigue damage. We look at effect of micro damage healing, moisture-induced damage, oxidation, and its coupling with fatigue damage. Some other subjects such as induction heating, rheology of asphalt, and finally software development. What I will be talking about for the bulk of this presentation is going to be constitutive modeling of rutting in airfield pavements. So we all know the problem. Pavements rut under wind load. Now, on the left, we see an alt pavement section, and these are done at higher temperatures, and we see a lot of rutting. In the right, we are looking at a heavy vehicle simulator in Arabic pavement testing facility, all codes of engineers, and these are some thin asphalt layers. And as we can see, a lot of the rutting and the permanent deformation actually occurs in the sublayers. So it is important to account for permanent deformation not only in asphalt, but in all the layers. Now, this is very important for thin asphalt pavements with very thin asphalt layer, but also for thicker asphalt layers, or we see that a lot of the permanent deformation comes from the granular layers and sublayers. So we need to account for that. To account for that, we look at viscoplastic model for the asphalt, and we look at elastoelastic model for the base, subbase, and subgrade. I'm not going to go through a lot of formulations for viscoelastic. Most of you are familiar with it. This is just nonlinear viscoelastic model shaped in 1969. There are some nonlinear parameters there. For example, nonlinear parameters G0, G1, and G2. And then we look at D, which is the compliance, and we have D and lambda n as the Perroni series parameters. So this is basically the viscoelastic component. To get the value of the permanent strain in asphalt, we use classical viscoplastic model approach by Perzina. Now, when we look at this, we basically have a yield surface here, F. And obviously, if the stress point is inside the yield surface, there's no yielding, no permanent deformation. And as the stress increases and it goes outside the yield surface, what happens is that we will have a hardening function that is going to expand and reach to that point. So Perzina type models are based on what we call overstress function. And what it really is, the overstress function is the distance between the stress point and the yield surface. The larger the distance, the higher the increment of the plastic strain. So we basically get our plastic strain based on that. This is just a figure of the yield surface in the J2, which is a second deviatory stress invariant versus I1, which captures the confinement level. And we see that if we are inside the line, lower than the line, where J2 is less than alpha I1, we have no further evolution of the plastic strain. And if we are outside of it, of course, we have evolution of the plastic strain. But this is for HMA. Now, there are details about how to implement it, how to calibrate it that I'm omitting here, but this is really the essence of the model that we use. For the granular layer, what we use, and then, of course, we have made some modifications, it is called a cap model. The only difference here is that we put a cap on it such that when the stress in the confinement level increases, material can undergo permanent deformation. But when you use classical modified Drager-Prager model, doesn't matter how much confinement you apply to the material, it will not show any permanent deformation. So the cap model will allow us to basically get permanent deformation due to several mechanisms. One is densification. You apply very high level of confinement. Another one is combination of densification and shearing, which is in this region right here. And then here it is mostly shearing because J2 is much higher than alpha I1. Now, we use this, we get some very good results that some of them I'm going to show. But one of the issues with this model is right here. There is a transition, and sometimes when you get there, it diverges and doesn't behave well. Another very important issue that is common for plasticity/viscoplasticity is that imagine, let's say, asphalt mixture. You apply creep recovery test. We don't change the stress level. but you just keep applying that. Now, if you look at the permanent deformation, you see that with each cycle, there is an increment of permanent deformation building up. Now, if you use classical plasticity or viscoplasticity, very fast, it saturates. So it says, well, the strength is not increasing, and then it won't increase. So for this sort of test, and we have a lot of this when we have tried running over our pavement, we can simulate it, such as very similar to create recovery and just continue it in a repeated manner. So it significantly underestimates permanent deformation. The deviation will be much more pronounced as we increase the number of loading cycles. And it is due to the fact that historians do not consider the effect of resting time. What happens when there is no load on the material? So we looked at what is called a hardening relaxation component, and we use it for both asphalt and another version of it to granular materials. So imagine some particles together, and let's say if you start loading it, and imagine this is, for example, base, then they become flatter, and the angle between the longest dimension of the aggregate and the horizon decreases, and then when we unload, there will be a little bit of rebound. This level of rebounding would be much more pronounced if we deal with asphalt mixtures, because you have binder, when you apply the load, you are squeezing that binder, and then it applies, when during the reloading, there is a lag, and it basically applies some stress to the aggregates to take it back. So the shape and the microstructure at the end of during the loading and unloading changes a little bit. And we think that that little bit might be enough for us to be able to capture the progressive increase in the permanent deformation. So to explain how the hardening relaxation works, let's look at a stress. Now on the left, we are looking at what we call hardening plasticity response, and here hardening relaxation. So at 0 and 0, there is a yield surface, nothing is happening. And then you load the material, the stress level goes beyond the yield surface, therefore the yield surface expands. The yield surface must expand such that point A is on the yield surface. Now when we unload, in the classical plasticity, the yield surface remains where it is. Doesn't shrink, and you go to 0. Now, for the hardening relaxation, we let the yield surface to shrink a little bit. And that is because we say that during the unloading, there is a little bit of rebound. Now, if you reload again to the same level of stress, what happens here is that, well, this is the path, you are in the yield surface, no yielding, and it shows no further increment of the plastic strain. But here, well, there is a distance, and that distance is enough to give you further plastic strain. So we use this concept, we call it hardening relaxation for asphalt mixture, and we call it hardening function, an evolving hardening function for granular materials. And of course, the parameters that we use are different. And we think that it is really, the mechanism are similar. It is more significant in asphalt, but of course, less significant in granular materials. So we did some prediction of the model for the experimental data. This is just for asphalt mixtures. And as you can see here, this is just classical theories, which just saturates after several cycles. But in experiment and with models, we can and prediction, we can basically get much closer. Another prediction that we have done has been for airfield. They use heavy vehicle simulator, And they are mostly interested in applying fighter jets and cargo planes such as F-15E or C-17 loads. And then we were able to get the response both in shape and also the value. Now, as you will see in all of my curves, and we are underestimating the response. And you will see that over and over and over. And I'll explain why we see that. Another one is basically NAVTF test sections. This is at National Airport Pavement Test Facility. The one that we looked at it is construction cycle 3. They apply both 4-wheel and 6-wheel gear configurations. And one of the things that they changed was to look at the depths of the subbase and see what happens if they go from 16 inches, 24 inches to 34 inches, and keep the rest of the structure the same. So we run our simulation, and we saw that obviously, and this is trivial, as the subbase thickness increases, the level of stress in the subgrade decreases, and obviously that should decrease rutting. So subbase thickness increases, subgrade rutting decreases. But basically, look at that. We can also look at the permanent strain evolution in those. See what happens to the deformation that is permanent. And as we can see, and this is 2D, and usually we do 2D first because it's fast, and you can, if there is any issue in the problem, you can just say, hey, this is not working, so we can modify it. And we see that it basically shows that as the subbase increases, the level of strain in the subgrade decreases. This is the same for applying to 4-wheel, but in a stationary manner. And this one is a 3D. We put all the 6 wheels on the pavement and apply the load. Now, there are so many things that we do not consider. I understand that, for example, shear or rolling effect or the slip between the layers, we do not consider those things because one of the, as I explained, one of the ideas is to make sure that get the response as far as possible. And we think that these are some of the reasons for underestimation of the results. But we also can see the evolution of the plastic strain in the different layers. For example, here we see in the base and subbase. And this is just model prediction. Again, we are underestimating it. And the reason that we underestimate this is that we are assuming that our granular materials are nonlinear elastoplastic. We do not consider any anisotropic behavior. And these are the things that, for example, Dr. Katamler, he has done a significant work on looking at anisotropy, and Dr. Al-Qadi has done a lot of work on rolling effect and the sleep. So now there is one idea of saying, hey, what if we just look at it, apply a factor and bring it up? So far we have resisted, say, well, I will let it be down a little bit. It is better than previous, but at least we are not saying that we are accurate. There are so many things that are still missing, and if we are missing them, then probably we are underestimating the results. Something that we are doing right now is to look at the NAV MRC test sections. They build the pavements with different materials. We are looking at PG64-22, 76-22, Warwick's and hot mix asphalt. And we have done some simulations, we got some good results, and this is just an animation of how you can relate the 2D to the 3D and the cross sections by using model. And I'm going to stop here for the models and look at the software development. So what I showed you, whatever model that we have, whether it is plastic, viscoplastic, viscoelastic, we used to use UMAT, user-defined material subroutine, use it with Abacus, and then of course you go to the lab, do the test, analyze the data, get the model parameters, and run your simulation. So you are basically using Abacus. Then we went to, so then we talked to FAA and they said that, well, we do not want to use Abacus. It's expensive, it's difficult to use and create all those meshes, and we want engineers to use it. Can you folks just develop a standalone? So we said, well, we know a few programming languages, and how hard could it be? And yeah, sure, we'll develop it. So we started working on that. And of course, it proved to be much harder than we thought. But the components that we have right now, we have Panda solver, GUI, which is user interface in Python. Solver is in Fortran. We also are making a C++ version. We have PPI, which is called Panda Parameter Identifier, which you can give it the data and get the model parameters out of it and run it. Now, what we have here does not depend on Abacus or any third-party software. And the interface looks something like that. So you look at what analysis type you want to do, what loading you want to apply, whether you want to do an application or demo. And demo just shows you how to do it. And then once you do that, you just say, hey, these are the pavement structures. We have some predefined materials to choose from, and say whether you want elastic, viscoelastic, or viscoplastic model for different layers. For sublayers, we can use elastic or elastoplastic. These are the two options that we have. And then here is what we call PPI, Panda Parameter Identifier. Let's say if you do dynamic modulus tests, one way is for you to create a master curve and get the current search parameters. But here you can just enter the data and run it, and then the program will give you the data required to run the analysis. Another important thing that we got from Farfield, and Farfield is the software that FAA uses for design. It has a very nice library of aircraft. So we got those aircraft and put it there, so we can apply different gear configurations and also create different user-defined. Let's say, for example, something like C17, it has some weird gear configuration, so you can apply that and do your analysis. And of course, if we are going to not rely on Abacus, we needed to develop our own visualization as well. So, and that is the way that you can look at the results. So all of those we combine in numbers. Now, this is just a flow chart that shows how all these works together. So I did a challenge, and one of my students is really good with doing creating finite elements. I'm sure that you are all good making very complicated models. So I said, well, you do the left one because you're the expert. I do the one on the right. Just enter. So basically what is happening, and the left one is 10 times faster. It is 10x, the one is 1x. So basically what is happening, we know that create this in Abacus, it needs a lot of expertise. You make a mistake, you need to run it and we come back and forth. And I said, well, you do it, and let's make a competition. And he was kind enough to accept, although he knew he's going to lose. So this basically shows that what happens. And the idea here is that this is, for example, applying the load. So here we say, hey, this is the load that we want to apply, and this is the level. But when you want to use abacus, you need to just go choose all those elements, make sure that you are not double choosing an element. So that is just to make sure that we are doing all these things in the background, but making it, but we don't want the user to actually see. And I'm done. This is still working on it, so I won't. So that was another subject. Now, I'm not going to go through a lot of detail on that and try to finish my presentation in time so I get a lot of, hopefully a lot of questions from you. So that is the second topic that we work on. There are other research topics that I want to touch on, and the reason for that is to see how can we use computation to get some of the responses. One of the things that we have worked on is oxidative aging. It is a very, very slow project. The testing is difficult for pavement, and we know that basically what happens to a pavement when it ages, right? We have a significant level of fatigue damage. One of the things that is important is how do you measure the material property for the diffusivity, like oxygen diffusivity? It is difficult. It is time consuming. So basically you need to force oxygen from one side of the material and measure how much you get from the other side. And even if you know it for binder or you know it for aggregate, then how can you measure it for mixture? Are you going to just put a mixture there, put pressure with oxygen? And so it is difficult. It is definitely not impossible, but very difficult. So one of the things that we do is that we look at the microstructure and run what is called virtual test. So we know, let's say, we have here a two-phase material, a three-phase material. One is aggregate, one is air void, and then mastic. Mastic is made of small aggregates and binder. So it is easier to understand what is the diffusivity of binder and aggregate. So we put it together and we actually run the test. We say, hey, let me have a concentration of oxygen at the top, and let's see how long would it take for it to pass the mastic. And once you have that, you know what's the diffusivity for aggregate, you know what is it for binder, you feed it back to your mixture, you run the test again, virtually, computationally, and you will be able to find the property of the mixture in terms of the diffusivity, for example. So here is a video of how basically this works. You introduce oxygen at the top and let it diffuse through the microstructure and see how long will it take, and based on that you can calculate the effective diffusivity. In this case we have 0.12 millimeters square per day. And of course when we say day, for us it is number one computationally, so we can do it in probably 5-10 minutes. Now we know what is the diffusivity of air void, coarse aggregate, and fine aggregate plus mastic. We just put everything together and run the simulation again. And if you do that, then you can come up with a value which is the effective diffusivity of the asphalt mixture. Is it going to be very accurate? I don't think so. Is it going to be closer to what it actually is rather than what we assume? Probably yes. And I think that little bit of getting closer is really what all we can do with these virtual ones. We do not do two-way coupling or even one-way coupling of multi-scaling. And the reason is that we really think that what we do at micro scale is for more information and insight, and we can use those to basically feed it back to macro scale. And then we ran some simulations, looked at the damage, and see what happens. This is 2D. And what we saw is that with number of loading applications, what happened is the damage migrated more to the surface as compared to the, so for example, here you have higher values here, but then here you see that the surface is gone, and this is the damage density. 1 means that the material is gone, 0 means that it is not damaged at all. Another study that we did was for thermal electromagnetic response of conductive asphalt concrete. This is again for Army Corps, ERDIC, and they called it, I think, hot mix on a pickup truck. Hot mix on a pickup. So say, hey, I mean, you want to patch a pothole. So usually what we do, we use cold mix. And then we said, well, I mean, how can we have a small amount of hot mix in the back of a pickup truck and fill these potholes better so they can last? So they were looking at what type of material to use, what should be the size distribution, what could be the grit blend, the percentage, and of course, when you mix them together, you apply it. It is very similar to put it in a microwave. So you apply weight to it, and then it heats and creates the hard mix instead of a cold mix. And what we were able to do, again, a very simple model, 2D. We created the gradation of the aggregates, distributed those particles in the mixture, and computationally apply electromagnetism to it. Of course, when you have electromagnetism, those steel particles, the temperature increases. Once you have increase in temperature, the temperature starts to basically affect the other areas. We will have conduction, and we see how fast we can basically increase the temperature of the mixture. And then we looked at the numerical modeling and the experiment, and they were close, and based on that, we were able to give them some recommendations. And with that, I'm going to conclude saying that permanent deformation in all layers must be considered for the rutting of flexible asphalt pavements. The classical plasticity and viscoplasticity theories cannot predict progressive increase in permanent deformation of asphalt, concrete, and of course, granular materials. And what we think is that microscale simulation can be used as visual testing to provide input for macroscale computational methods. The goal is to have a very nice pavement. And hey, if we do all this and it doesn't work, then I think we can just enjoy the stress in the pavement. With that, I would be happy to answer a question.
Questions for Professor?
Oh, thank you so much for the presentation again, Professor. I hope you can disclose this, but I was wondering, so your Panda solver, is it actually a built-in finite element analysis, or are you just retrieving data from pre-run cases that you have stored there?
No, this is, are you talking about the software?
The solver.
The software is the actual finite element program.
So so it means that you can actually output bits, not only main responses. So you can output strain fields, stress fields coming from the model.
Yes, imagine such as a very layman version of Abacus customized specifically for our structures. So we have, we do all the things that is done in a finite element software, such as basically checking the material model. We have the algorithm at the structural level, creating the stiffness and the inversing methodology and all. So it has all the components. So the main program is written in Fortran, but then the interface is Python. So the parameters that we need to use, we use Python and MATLAB to basically analyze the data, create the input file for the finite element, then we run it again because we make an executable file. So, for example, you don't need to have Fortran compiler installed or any third party. You can just run it. And thank you. Yes.
So thanks for your presentation. So I have, my first question is, you use Drucker-Prager, right? As cap model for the viscoelastic, the yield criteria. Have you ever tried any other yield criteria?
Other yield criteria, yes, we have. We have looked at many things that are used for metal, for example, like simple J2 class, and also we looked at the models that use look at the smeared cracks. The CAP model, even for example, the CAP model, it gave us very good results, but then gave us some divergence. That's why we ended up with going with the modified Drucker-Prager with a hardening relaxation or an evolving hardening function. I don't remember what other yield surfaces we used, but we looked at a few of them.
So if I may ask, one reason is whenever I think of this plasticity, the yield surface, at least for asphalt concrete, it's not really clear, right? Like for metals, we have done enough experiments to get your yield surface, and this for Drucker-Prager, it is very well defined for your granular materials. But do you think, or in a mind, that is there any way to identify the right yield criteria for asphalt concrete, which can, include all these specs?
Okay, so I'm going to answer your question in two parts. One is that yield surface, right? What I love about viscoplasticity is that you really don't need to stay on the yield surface all the time. Because one of the difficulties in computational plasticity is that whenever you get out of the yield surface, you need to kind of return your stress level back on the yield surface, and that is difficult. When you look at the viscoplasticity and Perzina type model, we know that at high temperature asphalt immediately yields, right? So instead of just making sure to take back the stress level on the yield surface, you just look at the distance, right? And that in my opinion makes it much more stable when you do the analysis. So that is one. So for the criteria, there might be other criteria, but I think something like Drucker-Prager has some of the fundamentals in it. First of all, some of the parameters, for example, the slope of the line, it is related to the angle of friction of the aggregate, so that captures that one. It is pretty obvious that our material is very susceptible to confinement level. The higher the confinement, it goes to the plastic region, not that fast. So it has all the components, I think. Now, can you use another model or another yield surface to get those or even better? Most probably, yes, but I think, Drucker-Prager at least has some of those, my Drucker-Prager has some of those criteria that are important in that matter. Does that answer the question?
Yes.
Thank you for the nice presentation, Professor Darabi. I was curious when you presented about the yield surface shrinking, can you walk through how does the model shrink, right? You need to define how does it define how much to shrink and what type of inputs is required to actually define that shrinkage of yield surface?
Yes, I can, yeah. So we got this idea about what people have done in this is okay. This all right. So this is the concept, right? But we got the idea from Uno, who did some work in plasticity of metals. Their issue was that at some point the hysteresis loop basically stops, doesn't move, it stops and they use what is called a memory surface, but in the stress space to kind of define that. For our case, we are doing something very similar, but in the plastic strain surface. So we define what is called a memory surface, right? And the and then look at how much plastic strain we have, and for how much of it we have considered the evolution or the contraction of the yield surface. Now, if you do, let's say, loading, unload, and just keep it remain unloading, it's not going to keep shrinking and shrinking. There's a limit to it, and that is based on what we call a memory surface. I can share some of the papers with you. So, but it is very similar to also the concept of the yield stress. So you go inside the memory surface, it doesn't evolve. You go outside of it, it evolves, but until you again come back inside or on the memory surface. So it is by defining a couple of parameters, and because we say that, hey, I mean the maximum amount that you can account for is that rebound here. So we need to account for that. I'm not sure if I answered your question though.
Yes, but I was just curious, like, what are the test parameters that require? So some of the details to define that memory surface, what are the requirements?
So the test that we use is constant loading time and unloading time test. So it is creep recovery, and we look at the progression of the plastic strain. Obviously, when we use the model without the memory surface, it just saturates, and then by analyzing those, we can get the model parameters. I hope I answered your
Yeah,
question.
thank you.
Yes. Actually, I'm building on the first question regarding the time temperature dependent material. I noticed in the last slide where you showed the thermo-electromagnetic model. Maybe my question is not that related, but when you showed the curve, the difference between the numerical and the experiment, we noticed after 400 seconds, the prediction is way different than the experiments. So I wonder how that affected your recommendation.
Okay. Thank you. So let me understand your question. So you're talking about the induction heating one, and after 400 seconds, the difference between experiment and prediction
Numerical.
becomes. Okay.
Like the numerical is already overlapping, it's way different.
Oh, these? Yeah, I mean, it's we can predict it, I mean, in an accurate manner. And the micromechanics, the way that we use it is honestly to rank order the material, saying that, for example, here, this one would be better than this. This one would be better than this one, or vice versa. But can we just use mechanical simulations to get the actual experiments? I'm not convinced that we can, because there are so many things that we are missing and we are not putting there. These aggregates escape. Like, I mean, there's friction. We are not considering those. Even in pavement layers, different layers, there is friction between them. Some of them are fully bonded, some of them are not. So I don't think I'm going to be too worried about trying to just get the response very clear, very close to the experiment. The idea was to be able to rank order the material and say which one probably would be better, and then you go to the lab, make it with that one, and with the material that the model suggests, and confirm it. When you go a couple of loops, a few loops back and forth, I think you get the answer that that is needed. Does that make sense?
Professor, I had a few questions about your oxidative aging model. Can you go to that one?
This one.
Yeah, but I think the slide in which you showed the profile showing up. The diffusion, yeah.
This one?
Yeah, this.
So here, the parameter that you're using is oxygen content in the binder.
So it is oxygen, normalized oxygen content at the top. We say it's 1. 1 means that it is basically that environment is saturated with oxygen. We do very similar thing with moisture. If you have fully saturated, we say theta, we call it theta 2. Theta is 1, which means that moisture is 1. Or here, oxygen content is 1, and then we let it diffuse.
I see. So now with this model, did you go to how it affects the binder in the profile? How it physically affects the properties of the asphalt concrete?
So we have a model that couples oxidative aging with viscoelasticity, and then damage model. Now, in the past, the way that we account for that was to incorporate the evolution of the oxygen content or the oxidation level to our damage model. But then we said, well, let's see what it does. And it is actually it's making the material harder and more brittle. So why won't we just go and change the compliance terms in viscoelasticity, which is those d sub n's. And if it is done properly, once you change the d sub n's and you have your damage model coupled with it without changing any parameter in the damage model, it should account for that response as well. So it should show you more damage. This is something that we have the draft and we are trying to submit. Before what we were doing, we had a damage parameter phi, and we were incorporating that aging level directly to that damage model and say, hey, that is, we can artificially increase the evolution of damage and make it faster. But the right way is to just go through the D parameters, I think. Does that make sense?
Yes, and I have just one more follow-up question. Do you think that this oxygen is enough to characterize and predict what's happening to stiffness in the model, or do you still see that we need something a little bit stiffer on the surface? Especially on the surface of a pavement, are we short on stiffness with this, or are you able to predict how stiff the surface is with this oxygen?
So I think, obviously, at the surface of the pavement, the stiffness or the modulus of the material should be higher because it ages and oxidizes much faster. Now, the idea of this is that we need to know how fast or how slow different locations in the pavement is going to age, which means that, but we don't know what is the diffusivity, the oxygen diffusivity of the pavement. Using that, we can get the oxygen diffusivity. Now you can create a pavement, put the oxygen on the top numerically and see where it goes. And based on that, you automatically you will have a stiffer layer at the top. And as you go down, the material becomes softer and softer. But I'm pretty sure, or at least I presume that experimentally, the layer at the top should be stiffer.
Thank you.
If we may ask just a follow-up to that one, just to understand, so this model you're showing us is not a coupled model, it's just oxygen diffusion, and then you take that output into a separate model that couples.
Exactly.
So if I may ask, please provide insights, why not do coupling at the very beginning and in this stage of the model to let, if there's how much of an influence is that diffusivity to the mechanical properties and feed that back into the diffusivity output?
But because it is getting so computationally expensive that probably we might be able to do one cycle, if we can do one cycle. We really don't want to use the microstructural modeling to get any performance prediction. The idea is to use the microstructural modeling to be able to estimate some properties without basically going to the lab, or at least get something close to it. But eventually, what we want to do is to just look at the model at the continuum level, at the macro scale, but use the parameters that we get from by considering the microstructure from the microstructural model, just to make it faster and probably getting similar results as well.
Quick question.
Professor, great presentation. I have a question. So you talked about the 3D model, like it takes a lot of time, right? So did you look into some ways to reduce the computational time so that we can overcome the 2D assumptions which we take in the model?
You can say that again.
So I was saying, like you said, a 3D model takes a lot of time. So did you look into ways to reduce that computational time so that we can so we can overcome the assumptions of a 2D model?
I think this is one of the motivations of that we went ahead with creating a standalone solver. For example, when you look at Abacus, it gives you options of, hey, do parallel processing, but that's very limited. Or does certain techniques that probably will work great for certain materials, but really, when we look at our structure in terms of just the geometry, our geometry is pretty simple. I understand that then we apply the load, but our geometry is pretty boxy, right? And we can do a lot of modification without our own code that is written exactly for that structure. So we do parallel processing. In terms of the stiffness, we try to just get rid of all the zeros by skylining and applying many algorithms. If we are, for these purposes, for the performance simulation purpose for pavement, we are a little bit faster than Abacus with UMAT. So.
Oh, I think that this ends our seminar for today. Does anyone have any quick question or more? Okay, so let's Professor about it.
It's set up for the